In this video, we're going to learn how to solve quadratic equations by factoring. You're first going to need to know how to manipulate some equations, and you also need to know how to factor quadratic expressions. Both of those are skills that we've hopefully learned, but we're going to review some of that before we get started. To start, let's solve these very simple linear equations. They really shouldn't take us long. We're trying to get x by itself. So if I add if I add 4 to both sides, that would isolate the x, leaving me with x equals 4. So if I plug in a 4 right here, 4 minus 4 would give me 0. And you'll find out later why this is so important. If I do it here, I subtract 7 from both sides, I would get x equals -7. And this one is a two-step problem. I would first add 5 to get rid of the -5. That would leave me with 3x equals 5. And then even though it doesn't work out perfectly, I would divide by 3 after that. That means x would have to be a fraction, 5/3. If I plug in 5/3 right here, after multiplying it by 3 and subtracting 5, that would become a 0. And then the last one here, similar setup, we're going to subtract 9, leaving me with 2x equals -9. And then we're going to divide by 2. That would leave me with the fraction -9 halves, or -4.5. So very important that we know how to do that. Hopefully that wasn't too much of a struggle. Factoring is not something that's necessarily fun to do, so I think it would be wise to only do it when we absolutely have to. We can factor to solve a quadratic equation only when there is a variable term, a quadratic variable term, and a linear variable term. And so this is a quadratic expression, and the quadratic term has the x squared, the linear term has x to the first power. So what we're going to do is we're going to go through these equations, and we're going to determine, if it's a we're going to determine if it's a good idea to try factoring this in order to solve. So we're going to circle each variable term and identify it as either a linear or quadratic variable term. So this one has a variable that is quadratic. This has a variable that is linear. And it says here, if the equation has only a quadratic variable term, then we wouldn't need to factor. It's really only when we have both a linear and a quadratic term that factoring would be worth checking into. So this one, because it has both, I'm going to say yes, let's try to factor that. We're not going to do that here, but that's the situation in which we would factor. Okay, this one has a variable that's linear, and this one has a variable, and that's linear. And then that means no. I don't need to factor for that. That's just a linear equation. This one has a variable. That's a quadratic term. This one has a linear term. And if I went over here, I would still see another quadratic term. I only need to see that there's one of each, and we do have that. So this would be a good one to factor on. This one has a variable. That's a quadratic term. I don't see a linear term, and so nope. I could factor this, but I don't need to. Let's look at the next one. This one has a variable that is quadratic. This one has a variable that is linear. And again, we have, I skipped one. We have another linear one here and a quadratic one here. Yeah, let's try factoring that one. And this one, different setup, but you do see a linear term within those parentheses. No, I don't need to factor here then. Let's go forward. Now let's take a moment to understand how can factoring really help us solve quadratic equations. We're going to start with understanding something called the zero product property. If I have two factors that I'm naming A and B, and their product is 0, what would have to be true? So I don't know what A is, and I don't know what B is, but I'm saying that if I multiplied those two things together, the result is 0. Well, the one thing that must be true is that if this is the case, then A would have to equal 0, or B would have to equal 0. Because if A was equal to 0, then 0 times whatever B is would be 0. And the same thing would be true if B was equal to 0. It wouldn't matter the value of A, but A times a 0 would give me 0. And that's called the zero product property. And we're going to use that to our advantage. Now, the only way that that's going to be helpful to us is if we have our equation set equal to 0. So what we're going to do with these three equations is we're going to rearrange each equation so that the quadratic expression is set equal to 0. And we're going to do this in a way that makes the A value of the quadratic expression positive. So maybe we have to review that a little bit, but the A value is the leading coefficient. So it's like the 4 here. This is the quadratic. This is the linear term. It says equals 7. I don't want it to say equals 7. I want it to say equals 0. So what we're going to do is we're going to get rid of that 7. We're going to subtract 7 from both sides. Be careful, though, because this minus 7 will not go with either of those two terms. So here's my new setup. It's going to say 4x squared minus 2x minus 7 equals 0. Now, this is exactly how I would like my problem to be set up before I would go any further. Notice that my A value is a positive and that we have it equal to 0. Those are the two things I really want. I'd also like it to be in standard form with my highest degree, then my linear, and then my constant, if those exist. So this one, we have 5x squared here. I would like it to be equal to 0 on one side. I'm going to do something a little different here, something that you might think of as a good idea. I am going to get rid of the 5x squared. I'm going to subtract 5x squared. But then I'm going to have to do that over here. Notice I put it off to the side because the 5x squared doesn't go with 14, nor does it go with 3x. I'm going to put this in standard form now. So first I would write negative 5x squared. Then I would put my 3x, which is positive 3x. And then I would put 14, which is positive as well. And on the right side of the equation, those would have canceled out, and now I have 0. This is set equal to 0, but there's one thing that I don't like, and I don't like that I have a negative A value. Well, what I'm going to do is I'm going to change that negative A value to a positive A value. I can do that by multiplying the entire equation by negative 1. This is okay to do because whatever I did to the left side of the equation, I would also be doing to the right side of the equation. My final answer here would be positive 5x squared, negative 3x, negative 14, and negative 1 times 0 is still just 0. So this would be the equation that I would use in order to solve by factoring. Okay, we have one more here. I see this negative A value. I'm just going to get rid of this 13x. It's just, in my opinion, fewer moves, so it seems easier. Let's do minus 13x. You'll see that there's not a linear term that this goes with, so I'm kind of just hovering it in the middle here. But I'm going to put those three terms separately. We're going to get negative x squared, negative 13x, and then minus 8, and then equals, and this will be a 0. Once again, I have a negative A value. You may have picked up, all you got to do is just change it to a positive, but then you'll change the sign of every term in the problem. You won't change the sign of a 0 because whether 0 is positive or negative doesn't matter. All right. Now that we have established a few ground rules, we're ready to go. It has been a little while since we've been doing any factoring, so I'm going to work this one out and show you that process. Step 1, is factoring a good idea? Let's see. Do we have the Q's and the L's? I see a Q term and an L term right there and there. So yeah, I think factoring is a good option. Step 2, prepare for use of the zero product property. We want the equation equal to 0. Well, in order to do that, I'm going to add 7 right here. So if I add 7 to both sides, this is my new equation, 4x squared plus 3x minus 10 equals 0. Now, step 3 says factor the quadratic expression. Okay, that is this part. That's the quadratic expression. And I'm going to factor that the way that we've done that previously. It may not always be so easy. I'm still going to equal it to 0 because this side stays. 4x squared. I don't know for sure, but I'm going to try 2x and 2x in order to achieve 4x squared. On the 10, I'm going to try a 5 and a 2. Now, this may be right, this may be wrong. You can wait until I've finished the problem to see if I'm correct. We have 5 times 2, which is 10. We have 2 times 2, which is 4. And if I subtract a 10 and a 4, I'm not going to get a 3, so that's not right. Even if I flipped around a 2 and a 5, I would still get the same stuff because these match. You know what? I may have made this mistake. Maybe it's not 2x and 2x. Maybe it's 4x and x. Now let's try doing a 5 and a 2. So we get 5x here, and we get 8x here. Now, if I have a 5x and an 8x, I can subtract to get 3. So that is the setup that I wanted. Good old factoring. Sometimes you got to work your way through it. I want a positive 3x. So I'm going to put the plus on the 2 because that would make the positive 8x, and this would be a minus. All right, now, the last part here is just like we talked about with that a times b equals 0. The only way that these two things can multiply to equal 0 is if a equals 0, 4x minus 5 equals 0, or x plus 2 equals 0. And now I'm going to solve these very simple equations like we did on the first page. I would add 5, and then I would divide by 4. So x is 5/4. Over here, I'm going to do the same thing. Solve for x. I would subtract 2, so x equals -2. And that one's finished. These two values of x, when plugged into the original problem, will make a true statement. Plugging in the fraction would be a little more difficult. Plugging in the -2 wouldn't be terrible, but if you calculate that, it will equal -7. And those are the only two numbers that do that. That's how we used factoring to help us find it. So that was the first one. It's going to be a little shaky. We need to see more of these. So let's keep going. All right. Is this a good problem for factoring? Do I see there's a quadratic? There's a linear. Okay, that's enough for me. Unless the quadratics were going to cancel out. These quadratics will not cancel out. So yeah, let's try this. This is going to be a good factoring problem. First, we got to get it equal to 0. What I'm going to do is add 5n squared. (3n squared) is the result there. We have minus 13n, and then we have minus 56, and then we have equals 0. Okay, it's equal to 0. Now I'm going to factor this side, still keeping it equal to 0. There are a couple things I do like about this factoring. This is a prime number, so I know it has to be 3n times n. And I also think 56 is consistently a 7 and an 8 that multiplies to give me that. So the question is it 7 and 8, or is it the other way around? Let's check it out. We're looking for subtraction, so 7n, and 24n. Well, that didn't work, so it's not that order. Let's go back and flip the 8 and the 7 around and see if that makes any difference. If I do 7 times 3, I get 21 in, and if I do 8 times n, I get 8 in. 21 minus 8 actually is 13. So that is how I want those numbers. And now I want to make sure that I get a negative 13. Well, the negative needs to go on the more powerful product. That was the 7 times the 3. If you'll recall, that was 21. So I'm going to put the minus here and the plus here. Once I have it factored, it's really pretty simple. You're going to take each of those factors and set them equal to 0. And then you just solve those two equations. And there could be more if there were more factors. Subtract the 8. So now you have 3n equals negative 8. And then divide by 3. N equals negative 8 thirds. So sometimes it's a fraction. Sometimes it's not. Like this one will not be, because I'll add 7 and I'll get n equals 7. And those are the two answers for this equation. You'll notice that that one went a little quicker. That's what happens as we continue to do these. Okay, is factoring a good idea? Let's look through our problem. We have a quadratic term. We have another variable term here that is also quadratic. And we didn't have a linear variable term. So it's a no. I could solve this problem using the same methods. Actually, there would be no point in trying to factor it without the linear term. But yeah, that's all it is. So no, I'm not going to factor. Not going to factor. We would solve this in a different way. This problem looks different. Is it a good idea to factor? Let's look. We have a quadratic term, and I also have a linear term. So just because it looks different, we are not going to approach it any differently. Yeah, factoring would be a good idea here. Let's get it equal to 0. Okay, I'm going to do the right side equal to 0. So I'm going to add 24n, and I'm going to add 24n to the other side, and we're going to get 8n squared plus 24n equals 0. This definitely looks different than previous problems, but we're on to step 3. It says factor the quadratic expression completely. Well, this doesn't factor the way that we thought it did, but this does have a greatest common factor. If I look at each of these two terms, I would pull out 8n, and then in parentheses, I would have a binomial factor, and it would be n plus 3. So it did factor. It was just a little bit different. What are my two factors? 8n and n plus 3. Set each of those equal to 0. So the first one would be 8n equals 0, and the second one would be n plus 3 equals 0. If you solve the first equation, you would do that by dividing by 8. Well, if I do 0 divided by 8, I'm going to get 0. The second problem, if I subtract 3, I would get n equals negative 3. Those are the two answers that would make the left side equal the right side. The process still works. Let's look at another one. We have a quadratic term, a linear term. Yes, I do want to factor. Let's set it equal to 0. I would subtract 72. Subtract 72 from both sides. And the more you do this, you'll start to pick up on some patterns. But this will say 6r squared minus 24r, and then minus 72 equals 0. I don't like that 6, but just like we did on the last problem, I kind of recognize a greatest common factor for those three terms. Yeah, and 0. I really am looking for 0, but 0 is divisible by 6, which all these other terms are divisible by as well. So let's take out a 6, and that will make my problem a lot easier. So if we factor out a 6, On the left side here, we're going to get r squared minus 4r and then minus 12. So 6, and then this part factors some more. R squared makes this problem a little bit easier. It's going to be r times r. And then I need to think about 12. What can I use for a 12 that can subtract to give me a 4? Well, when a is 1, like it is here, that becomes a little easier. And I know it's 6 and 2 without having to do all my multiplications to check it. I'm looking for a negative 4, which is going to be the negative 6 and the positive 2. And you're going to take each factor, including the 6. Okay, you're going to find out what happens with that 6, but you're going to set each one of them equal to 0. If 6 were equal to 0, then it would be a solution to this problem. 6 doesn't equal 0, though, so we'll just quickly boycott it. R minus 6, that equals 0 for a certain value of r, and then r plus 2 equals 0. So these are my three factors. I did try 6 equals 0, but it doesn't, so that doesn't work out. If you solve this one, you're going to get r equals 6. And if you solve this one, you'll get r equals negative 2. These are the two numbers that if you plugged into the original problem would work. Okay, and then the last slide here, just kind of showing you something else that could occur. Is factoring a good idea? Let's check to see if both types exist. This is a linear variable, and this is a linear variable, and so it appears like, factoring wouldn't be necessary. And that's true. Like, factoring is not a good idea here. But did you notice that this is already factored? It already says something times something gives me 0, which actually makes this a little bit easier. It's already factored. We didn't have to go through that process. We're happy about that. And so all I need to do is take this factor, set it equal to 0, and then take this factor and set it equal to 0. And I'll solve each of those equations. So you get n equals 4, positive 4 would work. And if I subtract first, I would get 3n equals negative 2. And then I would divide by 3. So I would get negative 2 thirds. Awesome. So we were able to skip steps 2 and 3 because it was already factored for us and set equal to 0. All right. We have the 5 steps here, but they are abbreviated. We want this to become a good, quick process. Is it good for factoring? Yes, I see both of my variable terms there. Is it set equal to 0? Yes. Let's factor. Let's factor. Keep it equal to 0 and factor this trinomial. Well, it's going to be a times a, 56. Again, I think it's 8 and 7. And then I get a plus and a plus because I got to get that 15 and that positive 56. This works out already. And very quickly, if I get really fast at this, you'll see that the a value that would make this a 0 is negative 8. And the a value that makes that a 0 is negative 7. And ladies and gentlemen, I have factored that problem in a matter of seconds. This is just an excellent thing to keep practicing. We did quite a few examples. Hopefully you're understanding it. If you have any questions, please let me know.